Hey everyone, welcome back for more Geodesy. So the second assignment is posted, and I'm going to just briefly go over what we're going to be doing, what some of the expectations are. The first problem is it's just worth a point, and it's just for you to go out and do some Googling and learn a little bit about some of the conferences, some of the events that go on in the world of geodesy. So the Intergeo Conference is an international conference, and if you just go to Google, read about it, and try to get some information just for our general learning. That one's pretty quick and easy. So the second problem, we're actually going to consider a theoretical USGS quadrangle. So hopefully you've all seen these before, the topo maps, the US topo maps. And they're usually a portrait rectangle. And they are 7.5 minutes, 7.5 minutes on each side. So that's a latitude and longitude change. So that's a delta psi and a delta lambda. And then what we're going to do is we're going to calculate m lambda of the north line. So m lambda of the north line. I'm going to make this bigger so I can write better. There we go. And the m lambda, the south line. So if we'll recall, m lambda is the distance in meters, feet, miles, whatever your linear distance unit is, along a parallel. So given that, we're going to ask what types of arcs are north and south lines, even though I just answered that. And then we're also going to get, we'll call it m psi of the east line and m psi of the west line. So the length of the lines when projected onto an Earth surface. So we'll get the linear distance, international feet, meters, whatever is being asked for, along the line of longitude between the parallels of our area. So that would be here. That would be our, let's see, maybe I can make this a little more. So we have our 7.5 minutes and 7.5 minutes. So if this is our map, then we can compute the m lambda of the north line, the m lambda of the south line, and the psi measurement along the longitude between the parallels of latitude of the east line, and then m psi of the west line. So we're going to get all those distances in the appropriate units. Then we're going to consider, we have the diagonal from the southwest to the northeast of our project area. So we're going to calculate the geodetic distance. That says geodesic. That's a typo. It should be geodetic. So on a spherical Earth model, use our typical radius, 6,371,000 meters. But then being sure to convert to proper units. So we're going to get the length of our diagonal from the southwest to the northeast. Okay, so once we have all of our m lambdas and m psis, or the distance in the real world of the sides of our rectangle, we're going to take those distances and then compute the theoretical dimensions of the map itself in millimeters by applying that 1 to 24,000 scale. And then once you've done that, you could actually go find a USGS quadrangle map, which are almost always in the 1 to 24,000 scale, and actually measure those lines and see how close you come to, in millimeters, to what those lines theoretically should be. Then we're going to compute the area of the map. Now, computing the area of the map, let's see, there's instructions that walk you through this, but kind of what we're doing, well, not kind of, exactly what we're doing is, so let's say we have our quadrangle here. And that lies on, the north is on some latitude and the south is on some latitude. So what we're going to do is we're going to compute the areas of the spherical cap that goes all the way to the North Pole, so it's like a hat. The spherical cap that terminates on the south line, so spherical cap. So we're going to have a big cap. I'll try to do that. That's the big cap. And then we'll compute the little cap. Change colors here. So then this cap, that's our little cap. And basically, once we have the area of those spherical caps, we just subtract. So we take the big cap, I'll say area of the big cap, minus the area of the little cap, I'll say LC for little cap. And what we're left with is the area of this band that goes all the way around the Earth, right? Well, our quadrangle is just a proportion of that, isn't it? So here's our quadrangle. And we just apply a ratio. Remember, this distance is m lambda, or delta lambda actually is what I should say. We want delta lambda here, our change in longitude. So if we take our, we'll say that's equals the area of our quadrangle, or area of a band. So the area of our quadrangle is just a portion of that, isn't that? So the area of our quadrangle in red on the diagram is equal to the area of our band, delta lambda. I'm butchering that, aren't I? So our delta lambda, or the longitude, the change in longitude that we move through, and of course that's just divided by 360, right? Remembering to always do our math in radians. And then we multiply that by the area of the band. If you think about it, it makes sense. We're just taking the area of the whole band, applying a ratio to get what portion of that area our quadrangle makes up. And then this all walks you through it. So what part C says, you can compare it just to know if your numbers are realistic. You can use this formula, which is an approximation. But it should be pretty close to the value you get. So if you get something that's completely different than this approximation, then you know that there's something wrong. So that's number 2. And number 2 is by far the most involved problem on the assignment, but it's really just an extension of what we did in assignment 1 and what we covered in the class so far. Okay, so then we move on to number 3, which again is an extension of what we've done so far with our LGH, or our graticule and height, and converting back and forth between that and our Earth-centered, Earth-fixed. So let's see, in this problem we're given initial Earth-centered Earth fixed coordinates for auger. And then we have these delta distances, right? So the change in our x value, the change in our y value, change in our z value. We'll use those to get, all those together, we'll get x, y, and z. So the Earth-centered Earth fixed coordinates of pub, station pub. And then for part A, we'll convert those to latitude. That's a terrible latitude, isn't it? Just make that a little better. To latitude, longitude, and r plus h. Just like we did in the first assignment. And then we'll calculate the chord between them. Once we have the x, y, z coordinates for each of them, we can calculate the chord. We could even just use the delta values to get that. So this is the chord between the 2 points. And we're going to do that for meters and international feet. Let's see. I guess I got a little ahead of myself. Part A, we're just getting the geocentric coordinates, so the x, y, z. So we're getting the x, y, z of pub. And then we're going to get the chord distance, and then we're going to get the latitude, longitude, and r plus h. So latitude, longitude, and r plus h. So what we're going to do then is we're going to look up the data sheet, which I can do right now. If you click on this, I can't click. There. So on this link, we will just, if we click on it, it brings up our an NGS tool where you can zoom to, if you click on the map, it'll bring you this, and you can zoom to the OIT campus. Welcome to NGS map, thank you. Have to zoom out and find Oregon, zoom down to the Klamath Falls campus, which is where Station Pub is. And it should be south here. There we go. So here's Station Pub. If you zoom into the Klamath Falls campus and you click on Pub, you can, it says data sheet, more info. And on the data sheet, so if I click it, it gives tons of information on Pub. These are published coordinates. So let's see if I can, let me bring it, there we go. So you'll look this up and look through the information briefly. And down, if you get to, what we're most interested is, where is it? Our NAD 83 latitude and longitude. Use the coordinates you came up with for pub, and you can compare to that position, and then you'll make some other comparisons too. But it's mainly just to get you used to looking at the information that's given on published NGS data sheets. Okay. So that's a simple, just a comparison. Let me bring up, well, where'd it go? Did I lose the assignment? Down here. So back to the assignment. So yeah, look up the data sheet and then make a table comparing some values, spherical and ellipsoidal positions, and then make a determination. So then number 4. The intent of number 4 is to try to get you used to working with the PLSS system. The PLSS system, our system of townships, ranges, sections, basically the inventory of public land that was sold off to pay for the Revolutionary War, and it's a system that we heavily rely upon now. Kind of get you used to how some of the calculations were done in the field for the PLSS surveys. So this problem, we're given a particular section within a township and some latitude, longitude values, and then we're going to make some calculations based on that and taking into account the convergence that we're about to go over. So let me just kind of draw this out. This will be helpful. Move that aside. We're not ready for that yet. Basically, if you recall, a PLSS township, I'm not going to draw them all out, but here's a township. And remember that there are 36 sections. So this is a 6 mile by 6 mile quote unquote square township. And we have 6 range rows. Or I guess these are township rows, and then range columns. And this is terrible, I know, but this is just a basic township. And what we're asked to do is consider Township 32, which is right here. And we're given the azimuth of the east line of the section and told that the intent is for the west line of section 32 to be parallel with the east line, but we're going to do some calculations and find and apply convergence and find out how convergence plays a part in the PLSS township. It's not that difficult of a problem. We're given azimuth here. We're given the south line, the latitude of the south line, and then ask questions based on that. So that's number 4. And number 5. So number 5, let me bring the assignment back up. So it talks about a solar observation, and we briefly introduced solar observations in one of the previous lectures. We're given that the azimuth to the center of the sun is 221.3715. We're given a semi-diameter correction, and then we're given an angle right from our back sight to the left limb of the gun, or left limb of the sun. These sound like a lot of things we don't understand, but it's actually, if you sketch this out like you should be with every problem, you're going to see it's actually really simple. So if we have a set of, I hate that. If we have a set of axes, I'll just use white, so get rid of that little mark. And if we have a set of axes, so here's our north-south axis, here's our east-west axis, and I'm just going to make up some azimuths and stuff here. I'm not going to use what's in the problem. But we have a sunshine, and for this example, we'll just say it's in the southeast quadrant. And we have a center, and that is a calculated value. So okay, so this is a calculated azimuth to the center. And then we have our instrument set up here, and say a back sight here. So drawing this problem out really is going to help. In fact, it's really, you can do it without, but visualizing it will help immensely, I promise. And our measured value to the left limb, which is the tangent line to the sun, to the left side of the sun from our perspective, we're given an angle right there. And we're given a calculated azimuth of the sun. And what else are we given? We're given this corrected value here too. So this is our correction to get us to the center of the Earth. And what we need to come up with for problem 5 is the azimuth of the backsite. So we can do a series of adding, subtracting angles to get that. Pretty simple. We've been doing that since plane surveying. Again, the key is to draw it out so you know what angles to add, what angles to subtract. You're going to find it's very, very simple. Okay, so let's see. That's problem 5. And then problem 6 is just another research type of problem. So just asking you to explain some different types of timekeeping. So sidereal time, solar time, UTC, UT1, DUT. We talked about all of those. But then there's a couple others, the TAI and the GPST. So do some Google research on that. Nothing that takes too long. Just briefly describe it and what sorts of corrections we would apply to interact with the other forms of timekeeping. And then, just like all assignments, discuss what you learned from the assignment, any difficulties you encountered, suggestions to improve. I do really get a lot from reading these discussions, and I do modify assignments based on these. So that's it. A lot of the information we've covered already, and what we haven't covered, we will cover before the assignment is due. So with that, let's go ahead and get into it. Convergence. So I'm going to use my wonderful artistic drawing abilities to try to develop an idea of convergence. So I'm just going to erase this. I'll just move it aside. Now, we learned from an example as well as from homework by calculating azimuths using the spherical triangle ideas, the properties of the sine and cosine laws, or the laws of cosine and sine, to get, if we have, let's see, a point A and a point B, and we'll just put them on the same parallel. And we have a grid north here, and we have a grid north here, and then our m lambda. And when we started out, and let's say our geodetic line is there. And when we started out, we actually used an azimuth. I'm exaggerating these values here. So this was the azimuth. This is the forward azimuth. And when we got to the end over here at B, let's give these letters A and B. And when we got over to B, we discovered when we calculated our back azimuth, it was not the 180 degree difference. It was about 5 degrees off. So this is actually that's not our back azimuth. Gotta make sure I do things correctly here. So our back azimuth, I should have used a different color, but remember it's the angle off the North Pole, so this is our back azimuth. And we would have expected those, once we account for the 180 degrees, we expect from plane surveying for those to be same. But what we discovered was over the length, and I don't remember what length we used in the example problem, but we ended up with about 5 degrees of difference in our forward and back azimuth. So what would happen if we did not correct for that convergence or the difference in those azimuths? What if we didn't correct those? What if we just followed a regular azimuth? What would happen? So let's say we are in a ship, a magical ship that goes through land and rocks and all that stuff. And we're on the Earth here, and we're trying to get from point A here to, say, New York to Britain, for example. And we set our azimuth here, and we follow it. Well, we're going to miss, because our forward and back azimuths are not equal, we're going to actually miss our destination. So we miss our destination by that much. We miss. And when we're on the open sea, that's a big deal. Miss destination. But let's say we're really dumb and we decide, let's stay on this course. We don't know that we've passed it. We have to hit our destination eventually. Let's just stay on our course until we hit it. Well, we keep going around the Earth, and then when we come here, we're not going to end up back at A, are we? We're going to end up north of that, paralleling that line. We go around the Earth, and we keep going and going and going. And really what we're doing is we're spiraling around the Earth, around the pole. And we'll just keep going around and around and around and around. And if we were infinitely small, we would spiral. We would never actually land at the North Pole. We would just spiral for infinity until we reach some sort of singularity or the laws of physics don't work anymore. So here's the pole. So that shape, the green lines here, is called a loxodrome, which we introduced that term earlier. So loxodrome. And it would be really inconvenient if we're on an exploration mission or a merchant mission to spiral the globe for all eternity until we disappear into a singularity. Not very convenient. So we need to account for convergence. So let's move this up. And I'll just say these, I'm going to use the word error here, which is a poor use of words because they're not really errors, but I'm going to use it. These errors are due to the effect of convergence of meridians. So we need to understand convergence. And going forward, I'm not going to say convergence of meridians every time. I'm just going to say convergence of meridians. I'm just going to say convergence. It just gets too tiresome to say convergence of meridians all the time. So that's what we're looking at today, convergence of meridians. So just for concept image purposes, let's take a look at what happens if we're moving along a parallel. And convergence happens whether we're moving along a parallel or, moving along a specific azimuth between 2 points. Let's say we have a point A here, And, oh, I don't know, we have an instrument set up. And at A, we have a grid north. Now, some of you might have thought, well, hey, if I'm not using a map or a projection, then I don't have a grid, so I don't have to worry about it, right? And that's not true. The second we impose a specific azimuth on our course, we've imposed a grid. We've imposed a system wherein we are fixing a grid north. So let's say we're moving to point B. Starting at point A, we take an azimuth, so we've imposed a grid north. And we're interested in this line along the parallel latitude. When we start out, we take a specific azimuth to B, right? And it's important to note that we need to consider, so this is grid north is our straight line going up. And this is geodetic north. This is that curved line, that curved green. I'm now doing yellow, but that curved green line is our geodetic north, pointing to the Earth, or pointing to the North Pole. And if we were to draw a line that is tangent to that curve at A, this is our actual instantaneous at point A geodetic north. So that difference in those angles is called, you guessed it, convergence, which we've been using C very shortly. We're going to switch to using gamma. I'll just put here C equals gamma. So C is convergence. And if we were to keep marching, let me just make some more lines here. So I'm just copying a grid north over. Grid north is always parallel, right? So these are all parallel. I'm just using my little parallel marks here. And they are all grid north. But what we find is as we march eastward, that convergence becomes less steep until we get here. And this is going to kind of be intuitive. Let's say this is our prime meridian. What that means is this is where our grid north equals geodetic north. So that red line is grid north equals geodetic north. And to kind of demonstrate that, if I had a globe here, and we have our lines of longitude coming from the pole, depending on our perspective, there is one line of longitude that appears to be completely straight. If we're looking head on, so this is the pole. If we're looking head on at our prime meridian, and then the lines start going the other way, don't they? So we can demonstrate that. So then over here, the geodetic north lines start going the other way and increasing in steepness. Hopefully your sketch is better than mine, but each of these have in each of these positions along the way, we have a unique convergence, don't we? Since the angle of that geodetic north to the grid north changes, so does the convergence. On this side, when our geodetic north is, let me think of how to phrase this. I think what we'll do, so consider just point A. The convergence angle is such that grid north, so, is east of geodetic north, right? So when grid north is east of geodetic north, convergence, C, is positive. So to the west of our prime meridian, convergence is positive. To the east of our prime meridian, here, convergence is negative. Or just to use our same notation, C is negative. There we go. So when grid north is, did I do that right? Yeah, I screwed it up. Just the positives and negatives, it's reverse. So when grid north is, let's see, here we have grid north. So I just drew it on the wrong side and gave it the wrong thing. So over here it's west. So you can tell grid north, my white lines on this side of the prime meridian are west of the blue lines. So when grid north is west of geodetic north, then convergence is, excuse me, negative. Sorry about the confusion. Hard to keep this stuff straight on the fly like this. So when grid north, on the other hand, is east of geodetic north, convergence is positive. There. That's correct. I'll just put here, grid north is east of geodetic north. So grid north, geodetic north. And we can see that there it's east of geodetic, grid north is east of geodetic north, and so we have a positive convergence angle. Okay, sorry about the screw up. So moving on, I will torch you with one more drawing. Well, probably many more, but let me just try to draw something here. Again, just kind of developing our concept image of what convergence is. And remember, lines of longitude converge. Our north on the grid is represented by parallel lines marching across our map. So parallel lines do not converge. So if this is our globe, or half globe, and we have the North Pole here. And let's say we have some parallel of latitude. So there's our latitude. And we have 2 points, we'll say A and B. We have our geodetic north and our grid north, which aligns with geodetic north at B, we'll say. So B is at the prime meridian. If I were to draw a tangent line at A until it meets that prime meridian, I guess I could have drawn my, there, that's supposed to be tangent. There we go. So the line tangent at A, that angle that we've just created, what would that angle be? Well, if I were to draw a grid north here, so grid north at A and grid north at B are parallel, aren't they? And if I were to consider, this is kind of tough to draw, but let's see. Since those are parallel lines and I consider that angle, we just got through saying that's convergence, right? Well, since my grid north lines are parallel, that also makes that angle convergence between my intersecting lines there. So that is convergence. We can use that principle to develop the idea. So I'll just say prime meridian here. We can use that principle of that being our convergence to start developing ways to find the angle of convergence. Okay, let me bring in my diagram now. You're probably tired of watching me suffer through drawing, right? Finding my diagram. There we go. And this diagram's posted on Canvas, by the way. A couple of things to note is the diagram, which came from a book, uses phi in place of what we've been using as psi. So I'll make those, you might want to make those corrections on your, so that's, wherever you see a phi, go ahead and change that to a psi. That's what we've been using, right? Okay, and in this diagram, we have our angle of convergence. Here's these tangent lines. Let me just so these are those tangent lines that I drew in the last drawing. From T to A and T to B are those tangent lines. So we've just kind of turned our model a bit. So this angle, change color to something a little more pleasant. This angle right here is our convergence, which is labeled C appropriately. There's a few other things we can glean from this drawing, or try to fill in some of the labels of the angles and sides. So since our radius here is perpendicular to a tangent line, remember radii are always perpendicular to a tangent line given a sphere, then we can say this is a right angle, and this angle here is our latitude, right? That's psi. From the plane, so this is the equatorial plane. This is nothing new. So that makes our angle from grid north to our, let me use a different color there. Let's see, there, and then our grid north to the line OA. Wouldn't that be 90 degrees minus psi? And we've seen that before. So if that angle is 90 minus psi, and the angle at A here is a right angle, that's 90, and they have to add up to 180, what does that make this? What would that be? Let's see. So the angle at A is 90. The angle at O is 90 minus psi. And then the angle at T, if we add those up, they equal to 180. And if we solve, we get psi equals this angle here. So that's convenient. We can use that information. So we have convergence. We have latitude represented in different ways. Yeah. So let's use that diagram with those labeled angles to develop a method by which we can calculate convergence. So note that you will see different formulae for calculating convergence, C. The reason for that is because the concept of convergence goes back hundreds and hundreds and hundreds of years. Well, in comparison, the pocket calculator is a brand new device. It was not convenient to calculate the convergence angle exactly, so different methods of approximation were developed which would suffice given short enough distances. And what we're going to do is we'll start out with the exact method. And I kind of made it up, so we can see what that is. And then we will go through and calculate a couple of methods of approximation. Now, let's see, I'll just write exact method. We have an opportunity here. I'm going to draw a new red line. And if we consider the chord between A and B, so here's A, here's B, and we consider the chord between A and B, the chord distance does not change with each triangle, right? A chord distance from A to B is a chord distance is a chord distance. Who cares what the spherical components are, right? So we can work with regular triangles. And let me just review something from plane surveying, and that is the idea of the long chord. If you'll recall, if I have some arc and 2 points on that arc, I mean, you could even think of this as horizontal circle, laying out horizontal curves like from route surveying. And there's a radius of that curve. Say we have point A, point B. I'm just developing the idea of chord distance here. And we have a chord from A to B, and we have an arc distance. Now, we've said before, and let's just call this angle theta. We could call it anything, I, whatever. We haven't used theta much, so we'll call it theta. And let's call this S. And let's call this, I don't know, CH for chord. Then we know that S equals, oh yeah, and we have a radius of R here. S equals R theta. We've looked at that many, many times, making sure we're using theta in radians. Well, the chord, if we remember from plane surveying, is equal to 2R sine theta. So that's the general form. Oh, sorry, it's theta over 2. That would have been a big mistake. So 2R sine theta over 2. We can use this formula to develop an equality from our diagram. So if you look, we have two triangles here. We have the triangle of O, A, and then back to B, and then back to O. So that's one triangle. And then we have another triangle that is T, and then A to B, and then B to T. So just to write that down, we have triangle OAB, which is centered at the center of the Earth, and we have triangle TAB. So I'm just going to erase some of this so I can keep working in the same spot. So we're going to use the long chord to motivate an exact definition of convergence. And what we've done is we've considered we have two triangles that share a side. So two triangles that share a side. And I'm just drawing this in 2 dimensions. We have O, A, B. Sorry, you can't read that very well. And TAB, right? There's our two triangles. So if we can get a chord length from each of these triangles, then we can set them equal to each other and solve for C. Let's do it. Okay. We can label a couple things on our diagram, right? On our the little diagram I just scribbled out. So looking at this diagram, our triangle OAB, that side is R and R, and this angle is delta lambda, right? The change in longitude. Sorry, I want to use a different triangle than that. Let's use we could use any of these, right? Let's use this one. Chord, there we go. Can use that triangle, and for that triangle, consider just DAB. So we're going to use DAB instead of OAB. So let's see. Chord AB in triangle DAB is equal to 2 times r cos psi, right? Because that's our radius length there, r cos psi. So 2 times r cos psi times the sine of delta lambda over 2. This is our delta lambda. So that's one value. The other value, or the other formula, if we were to use this r cotangent psi, so the length of this side of our tangent is equal to r times the cotangent of psi. And I'm not going to derive that. You can derive that if on your own. I encourage you to do that. It's super easy. It falls right out of the triangle relationships where the right angles are. And I can show anybody that if they want to. It's like 4 steps, super easy. So in that triangle, we have 2 times our length of a side there, times r times the cotangent of psi, times the sine of our subtending angle, which is c. So c over 2. Just working with triangles. This is baby stuff. Well, since the chord from A to B it's just a chord from A to B. It doesn't change length like a curve might. We can say that we can set those two equations equal to each other, couldn't we? So now we're into just solving equations. I'm going to move that up, and we can say if I take that formula and set it equal to that formula, we can solve for c, right? So I have 2 r cos psi times sine of delta lambda over 2 is equal to, and I'm going to continue it down here, 2r times the cotangent of psi times the sine of c over 2. We're going to solve that for c. It's not that tough. If I take the next step, just move stuff to the other side, I end up with 2r cos psi, this is just baby algebra, times sine of delta lambda over 2 over 2r times the cotangent of psi equals the sine of c over 2. Well, right off the bat, we can simplify this, right? 2r goes away. They cancel out. And we take the arc sine of both sides. Move that up a bit so I can do this. And we have the arc sine of that first mess, the cosine of psi times the sine of delta lambda, change in longitude over 2, all over the cotangent of psi. I hope you're solving this with me, so if I make any mistakes, you can correct yourself or correct me. And that equals c over 2, because we took the arc sine of both sides. And so what we get is c equals 2 times the sine inverse of the cosine of psi times the sine of delta lambda over 2 over the cotangent think I got everything there. So that is an exact formula. And then we could further simplify this by using the definition of cotangent. So I'm going to say through the definition of cotangent, then, which is cosine over sine, this reduces to C equals 2 times the sine inverse of the sine of psi times the sine of delta lambda over 2. And if you don't believe me, work it out. Super easy. So there we have an exact formula. Now, why do we bother with approximations if we have the ability to use an exact formula? Well, remember when the PLSS system was going on, or if ships are traveling by sea and they're having to regularly determine or calculate what convergence is, this is a really tough thing to figure out without a calculator. You have sines, which you have to look up in tables, and then getting the arcsine of products of sines was not something that was very easily done back then. And so that's why we come up with approximations. So next time what we're going to do, so this is the exact, and I'm going to preface moving forward by saying we're not going to use the exact formula because we need to be able to reproduce results from history. Since they didn't use it throughout history and BLM still doesn't use it, they use an approximation. We'll next develop an approximation that's much easier to program or to calculate. So I think I'm going to leave it there. I was hoping to get to the approximations, but that is convergence. That's the beginning of convergence. Next time we will actually develop the approximation, then we'll run through an example of convergence before we move into the ellipsoid. All right, so enjoy the rest of your day, and I will talk at you later.